So FEA sanity checks. If you're going to do a full set of checking on FE analysis, I've on here talked about sort of like a full survey chronology, and that breaks down into what you're going to be doing to produce this high quality report, convince first off yourself, and everybody else that you're doing a good job. So checks prior to analysis, all the boring stuff, got the right material data, you've sourced all your information and so on. As it happens, I've just got a consultancy project came in a couple of days ago, so I'm going through this right now, and it is boring. It's like get everything together. Then as you start rolling, there's checks we can do in the preprocessor, so element quality checks and so on and so forth. And then a couple of what I call auxiliary checks, analysis checks. My favorite here is the check for normal modes analysis. We flip to normal modes analysis, see if the structure is hanging together. Then there's checks which the solver goes through. So these are the rigorous checks which it does as part of its process. And then finally, it's post-processing checks where we get into and produce kind of like our full report. What I'm not going to be doing in this presentation is talking really about this. That maybe we'll do that on another video call. But basically what I'm talking about here is the quick, as I've called it, sanity checks. Which somebody mentioned on the kind of warm-up. Maybe I call it insanity checks. That's maybe a good point. So what we're looking at here is the sanity checks, which we're going to use. And I'm focusing here on linear static analysis, just to make sure we're on the right track. And the idea is that these checks are very basic. They don't prove the answers are right, but they hopefully will show if they're very wrong, if we've got the wrong idea, something fundamentally flawed with the model. Now the results are going to be loaded in the post-processor after we run this analysis. What I'm looking for then is initial checks, these sanity checks, that should be taking no more than like 5-10 minutes. Is everything in good shape? And then we can go on and do the full structural response survey. All the things I talked about in the previous slide, we can then kind of go through those, build up the full model response and so on. I certainly find that with producing a report with all our detail of what we've done requires obviously lots of pictures, lots of screen grabs and so on. And I've certainly got caught out spending 3 or 4 days preparing this report, and in terms of the results coming out the back end. And then you get towards the end and you think, hang on a minute, what was that value there? What's that stress value? What's that displacement value? Oops, there's something gone wrong here. Then you realize there's a fundamental error, and there can be many, many different types of errors, and we'll just touch on some of them, which if you'd headed that off, as they say, headed off at the pass, then we could have done a better job. So basically we could have stopped it and said, okay, there's something wrong with the analysis. Let's fix up what's going on. Let's debug it, get it sorted out, and then rerun it. And when we're happy, then we can kind of settle down and do the full report. And I've certainly, in chatting to people and reports I've seen, that can happen. We've gone straight in. We assume that the results are okay. Build up this full comprehensive report. So the idea is, let's head this off. Let's do a quick sanity check. And on the intro to FEA class, which I teach, I try and sort of emphasize this is really important, because otherwise we're going to lock up a lot of our time. So what can we get done in, say, 5 minutes, just to like a go, no go? Is this analysis good enough to start to dive in, deeper into that? So I'm going to focus here on checks which are really talking about displacement levels, if you like, and then also stress levels. So I've limited it to displacements and stress. Again, I do emphasize there are many, many more checks. We can talk about rounding error checks, load balance checks, all those kind of good stuff. Again, we can talk about that later on. I'm going to focus on this. So think of it like a 5-minute quick grab. Does this model make sense? So the first one we're going to look at then is displacements, maximum displacement analysis. Is it sensible based on engineering judgment? Now, is it sensible? We can actually look for the maximum value. Sometimes it's like a data probe. Maybe we'll see it on like this is a color contour plot, deflections. And again, watch out for the contour plots, because you can say, well, there's the maximum deflection. That looks good. But then go and look at the number here. Is it the right number? Is it microns? Is it meters? Is it something that we're looking for, the right kind of level? We can animate it because, again, animation is very useful because if we look at a static plot like this, maybe there's something else subtly going on. If we animate it, the brain can sense motion much better than just sees a static shot. If you kind of watching out, look in the garden, and there's like a bird flies past. If the bird's just sitting in the tree, you probably won't notice of it. If it flies past in your peripheral vision, you're suddenly going to get attracted to it. So it's this kind of idea. And spin the model around, really kind of rummage around the model, explore it, and you're looking for things which look unusual. Now, some of the errors can be cracks in the model, badly connected parts. We're also interested in unusually flexible and stiff regions. So flexible, maybe it's not connected in properly. Stiff region, maybe it's over constrained. We've connected it to ground by mistake. A contact has gone, it's bonded contact instead of make or break contact. Well, that would be more nonlinear analysis, but that kind of thing. Incorrect boundary conditions. I meant to constrain that, I didn't, or that region is over constrained. So lots of reasons why this should occur. And we'll dive into a couple of these in more detail. Now, I do a course called, online course called Manager's Guide to FEA, and I sometimes come out and teach this live. Now, the principle of this course is to teach a manager or CEO or whoever is kind of at the top level there to get a little bit smart about asking questions. Now, this guy typically is not going to know anything about analysis, but if he turns up in the design review meeting or the analysis review meeting, he can ask a couple of key questions. And so based on this, one of the key questions I kind of teach these people to ask is, well, you know your industry, you know your product. So have you got something like an A380 wing, something which is pretty flexible, or you have got something like a CNC bed, which is going to be definitely quite stiff. So we know that the A380 wing, there's a little guy standing here, I guessed he was about 2 meters tall. So scaling him up, I get about 8 meters deflection on that wing. And that's a pretty reasonable result. I'm looking for 8 meters. If I get, let's say then compared to the CNC bed, we want that to be as stiff as possible because we don't want to have flexing of this bed when we're machining something. That's going to obviously cause all sorts of issues and problems. So one's going to be dealing with meters and the other one's going to be dealing with microns. For those of you in the US, a quick conversion here. So 6/8 to 48, I call it 50 feet. So 50 feet, that doesn't sound quite right. It's 25 feet, I do beg your pardon. So 25 feet versus just microns here. So if I see microns coming out the A380 wing analysis, something very wrong has gone on. And if I see something like millimeters or inches or even bigger than that coming out the CNC bed analysis, something very wrong has gone on. So I teach this guy to ask at the design review or the analysis review, excuse me, what's the maximum deflection you see in your model? And that's all he wants to know because I've kind of taught him that that's a critical value based on the kind of industry you're in. And whenever I go and teach this live, I kind of do a survey, I ask the guys, you know, what's the product? What level of deflection do you expect to get out? So here we're looking for that number in the FE analysis. Now it's not a definitive check. I don't know if the model is right or wrong, but that order of magnitude is clearly identified. I've actually had some feedback. Some of these guys, the senior managers and so on, have actually appeared in design review meetings or analysis review meetings, and they've asked this question, and everybody, there's like a sudden stunned silence. How come he's asking this really smart question? And a couple of times we've actually had feedback that when an independent consultant, an external consultant comes in, they want to get on and do the dog and pony show and explain all the complexity of perhaps a nonlinear analysis and so on. And this guy's job is to sort of say, whoa, hold it. Before we go there, what's the maximum deflection you see in your model? And it's like, okay, it's taking us back to like reality. And so it works pretty well. So I recommend that somebody was calling in saying they don't know very much about FEA. Hey, you know your product. You know your product. So that's our first check. So first sanity check, is the number about the right order? Again, no calculations, no nothing, no knowledge of engineering FEA needed. So that's my starting point. And that's a great way of actually starting to kind of filter down the result. So why could that occur? Well, In my modeling, I've seen huge numbers. I've seen kilometers, thousands of miles of deflection and so on. A lot of you will have seen the same kind of thing. So there's two little examples here. If I put Young's modulus in with the wrong value, if it's a determinate structure and it's not a nonlinear structure, then basically, in fact, if it's an indeterminate structure, but it's a linear, then the stresses are going to look okay because the stresses are looking essentially at relative displacement. So stresses might be okay. If you just do, for example, a rod and just say pull the rod, apply the force, stress is force over area. There's no stiffness calculation effectively in that. And then you look to see, well, what's the deflection? And if you put Young's modulus in wrong, then you've got that stress level at a huge deflection. So a typical thing is if we use gigapascals, just thinking of European units for a moment. Now, if you think that that input box in your preprocessor is demanding the input in gigapascals, Young's modulus for steel, so you put in 180, in fact, it's actually requiring fundamental units. You've implied 180 newtons per meter squared, and it's actually 1 e to the 9 that is actually required. So you're at a factor of 1 e to the 9 out. So that's going to be a huge deflection. If you're too small, that means you're going to get deflections of 1 e to the 9 out. That's where possibly your CNC machining machine is going to start deflecting as if it was an Airbus wingtip kind of thing. So every element stiffness terms involves Young's modulus. It's proportional to Young's modulus. We assemble them together. Everything's proportional to Young's modulus. And so the deflections, when we invert that and get the solution out, that's the kind of thing that's going to happen. One of my favorite hate things, if you like, one of my things I love to kind of go on about is there's a lot of software out there will say we can stabilize any potential rigid body motion by putting weak system springs in. Now, this is quite popular in nonlinear analysis, but I have seen it actually people using it in linear analysis. And it's basically where we're getting close to rigid body motions, or we got rigid body motions. The solver detects that, and rather than giving a hard diagnostic saying, tough luck, I can't solve this because we got rigid body motions in here, you need to go and do some kind of debugging. It says, don't worry, I'll handhold, fix it up for you, and put these system springs in, distributed throughout, and it's doing it kind of automatically, so you don't know where they are. And then we can reach equilibrium because we got these springs in. And I have literally seen about 30 to 40 kilometers deflection because the stresses again could look okay, but this thing is in balance. Imagine a weak spring. The whole thing is in balance after, because it's such a small spring stiffness, we actually achieve balance under the loading with many kilometers of deflection. And the trouble is, if we just say sort of like 1e, well, let's say 19e to the 3 meters, well, that's actually 19 kilometers, and it doesn't necessarily kind of resonate. We're just looking at numbers. So I've actually seen those come through. I haven't actually done that myself in a report, but I've certainly seen external reports where stresses look okay. Whoops, hang on a minute. Do you really mean 19 kilometers deflection of your structure? And it's a CNC machine, or even an Airbus wing. Even that an Airbus wing at 19 kilometers would be a little bit much. So here's an example. This was a structure I ran, and I had issues with the CAD model. And basically, I had used a contact surface in this particular case to connect these different strips together. Due to the fact that mid-surfacing and offsetting and so on coming through from the solid geometry, when I wanted to do mid-surfacing or extreme surfacing, it was easier, I thought, to just bond everything together. Now I set the tolerances wrong in the bonding. So a couple of things happened. First off, it wouldn't run in a linear static analysis. So I'll talk more about this at the end. My favorite way of checking a model, and I would say really now part of my sanity or insanity checks, is I almost always now, even before I launch the static analysis, I run an auxiliary normal modes analysis just to see what I've got. In this particular case, I'm forced to because it won't run as a static solution. But if we turn it into a normal mode solution and make sure we've got density on the material properties, we've got a stiffness matrix, we've got a mass matrix. We're solving that dynamic matrix, which can solve for rigid body motions. And hey, here are three views of this strip on one side is not connected at all. So the whole thing is just kind of floating around. Now that would be a hard stop for a static analysis and it would fail it. This one is a little bit more subtle. I'm getting elastic modes, and some of these actually showing, like this strip on the right-hand side, it's connected at one end and connected at the other end, but it's not connected in the middle. So that's the kind of thing we want to spot. Now, if as I've suggested and look at the display shape plots, you might not pick that up. If the load path isn't particularly through that, you might not notice that that basically lack of connectivity in there. If you do a normal modes analysis, here I've got elastic modes 4, 5, and 6, but let's assume that I hadn't got the rigid body modes, 3 of them. Then that would be elastic modes 1, 2, 3, 4, and so on. And as we're going to see another example, as you go up the modal range, the mode shapes get busier and busier and busier. And sometimes it's the busy mode shape, the complex mode shape is actually going to show you where something is broken down. And I'll show you a slide of that coming up very shortly. So a very, very useful check here just to see what's going on. This again is a normal modes analysis. This was interesting. This was a kind of a combination of training and also mentoring at a particular client site. So this was a bunch of designers, and they were producing this platen here, for example. It's all solid steel sheets, and it's fillet welded together. For the design, there's no reason to actually model the fillet welds. They're just called out, and they're not necessary to put in. So when we ran the first analysis, and I'm kind of doing this live, again, it failed as a static analysis, so put it through a normal modes. And here we can see a couple of scenarios. Now, these tend to be the higher order modes, which are showing this. What's happening here is this little kind of gapping that's occurring here in this top left is due to the bottom left picture, where basically the only point of connectivity between the solid geometry is at the corner there. The fillet weld is not modeled, so there's just one node gets merged in there. So we see a sort of a gapping, or not a gapping, a sort of opening up of that corner. We're literally peering into that corner as it opens and closes. So that looks very odd. This one was an even higher mode shape, and it just happened to catch that edge passes over that edge, and it was a busier mode shape, higher mode shape like this that showed it. In that particular case, what was happening was the fillet weld was at some intermediate point, so no node got connected between there. So that mesh and that mesh didn't join up, so we're getting that kind of motion in there. So that's the result of not modeling the fillet weld. Again, that ran as a static analysis, but I wanted to see again what's happening there. Just check it out. So that was, and we'll revisit that, and I'll show another little thing that we noticed on that particular case. So that's the deflections. Now let's look at stresses. And again, the idea is thinking of this manager's check. And basically, I'm going to look at the maximum stress. And I might as well look at von Mises stress because that's pulling everything together. Later on, I'm going to look down at component stresses, maximum principal stresses, and so on. But at this point, I just want to get a snapshot of where that maximum stress is. And again, spinning the model around. I also like to control the legend here, or the levels. So rather than just accept the highest level, I might well put this down to say yield a level, and then as red the top value, and then say, well, what's higher than yield, or something convenient. I don't like to just have whatever peak value there is the top of the scale, and then let it kind of do what it wants to do. I want to be in control of that contour, say this is the level I'm considering, what's above and what's below that. So a couple of things we're going to talk about in a little more detail. One is, are the hotspots high stress in the regions you expect? Are the stress jumps acceptable? We switch off stress averaging. We look at this local hotspot or high stress region, high stress gradient. Do we see big jumps across the element, which would mean perhaps we've got maybe meshing problems. We need to do mesh convergence, whatever it might be. Maybe we've got high stresses due to what's called modeling features. So I'll expand on some of these in the next couple of slides. So again, this is something I'm going to teach my my engineering manager or my manager. What criteria can we apply to stress? Well, again, we're going to pull off that peak stress. What's the biggest stress you've got in your model? So this is his second question when he's kind of doing a review. Okay, yeah, okay, I get all that, but just tell me for a minute, what's the biggest value of stress you get in your model? The reason for asking this is, if it's a linear analysis, if we've got, for example, our biggest stress in the model is, say, at this value, then we're below yield, and that's okay. Again, we're not getting into the actual uh, detail. We're not doing like a verification mathematically to say this stress looks okay from a sort of our equilibrium point of view and so on. We're just again using our knowledge of the material in this particular case to say it's a linear analysis. Those stresses should be below yield. If they're not, they're above yield, which is the case in here. The stress is unreasonable. This diagram is immediately below in the middle here. And basically our maximum stress in the model is above the yield stress. Now that can't physically happen. There's two things have potentially gone wrong. There's an error in the model. For example, loads are wrong, cross-section areas are wrong, all the what I call finger trouble, things that we've typed in wrong or got our data wrong, or maybe more unfortunately, the model is actually under strength, the design is under strength. So again, it could be one of those. But either way, it makes no sense to have the stress bigger than yield stress if we're pushing for a linear analysis. So if it is, then a big warning goes off. Equally, if the maximum stress in our model is very low, say only say 5% of yield stress, and it's supposed to be an efficient design, it's supposed to be a load carrying design, let's say, then we've not got a very good design again, or we got finger trouble. Now, some structures are stiffness driven. So, for example, like the CNC machine block, it might well be that the maximum stress is way down, but we know that. So again, we know our product. So again, this is the kind of thing we're thinking about. Now, remember the ratio of ultimate stress to yield stress in typical materials, metallic materials we're using, is going to lie somewhere between 1.4 to 1.6. In fact, the classic aerospace ratio of limit to ultimate of 1.5 came back from the early days where using aluminiums, where that was the typical kind of ratio. So that's where that scaling factor came from originally. So the physics is saying we can't get much more than 1.5 1.6 times the yield stress, even if we did a nonlinear analysis. So stresses bigger than this physically can't occur. So it's very embarrassing when we report these in the analysis. So just to kind of emphasize this, this is our yield point in here. This is our ultimate strength point. We're talking about ratios of, say, 1.4 to 1.6. I can't find the drawing tools on this, unfortunately, but basically, linear analysis is just going to kind of shoot straight up here and just keep on going. And I've seen stress levels reported 6 or 7 times yield stress, which is just physically kind of meaningless. And if you don't kind of make a note of that or mention it, and you actually let that report go out, it's like, well, does the analyst not understand the implications of 6 or 7 times yield, or whatever it is? So if it's there, and I'm going to come across a couple of reasons why it might be there in the analysis, and we might sort of say, okay, justify it. But again, we need that justification. We need the background story of why that's going to be the case. Here's a stress concentration, and this is a classic shape. It's a shoulder. So there's a known stress concentration factor where I've put the curved fillet radius in. Deliberately here, I've taken that fillet radius out, defeatured it. And now we've actually got a mesh-dependent stress level. So this is my FEA feature. If I forget to defeature, or I deliberately defeature, then I'm going to get very high stress in here. This in the diagram here, the graph, we go up to the nominal stress, which is occurring. It's the kind of the darker blue and the lighter blue. That's essentially hovering around the nominal stress. Get to this little corner in here, and I'm way above the nominal stress. I've actually got a singularity. As I put more and more elements in there, that singularity is going to get stronger and stronger. So if I've got a feature like that, I have seen people sometimes quietly move another part of the structure in front. That's kind of a little bit of a gray area. Shouldn't really be doing that. You should be exposing that and saying, okay, it's there. It's an FEA feature. Trust me, I'm an engineer. It's not an area of importance, and I'm going to allow it in there. But there's a justification. There's an explanation in the FEA model. So maybe that's why we get stresses, say, 3 or 4 times yield, but we explain why we're there, why they're there. one little thing that can catch us out is like just a simple coupon test. I pull here, I expect Poisson's ratio shrinkage across the width. At the left-hand end here, I've over-constrained it to ground. I've stopped this shrinking in the vertical sense. So what we've actually got is, again, a single point reaction there, and that's another singularity. So there, I might say the stresses are important over here, this general region. Okay, I've done a bad modeling job there, but we talked about some Venant's theorem last week. Maybe I just say this is the area of interest. We're going to let that go, but I still want to explain it. I want to put in the report why that's occurring. The reason it is occurring because I've done a very bad representation of the boundary condition. The actual boundary condition I want to be modeling is on the left-hand end here. What I'm trying to do is have part of the coupon, overall coupon, so our gauge length here is free to shrink at both ends of the gauge length. And we've actually got the transition, the grip length, and so on well away from the actual gauge length section. So this is what we're trying to model here. This is the boundary condition we're trying to model here, not gripping the actual gauge length here. We would never do that on test, but here in the FE analysis, we're kind of implying that. So that's what we want to set up. And the blue here is just a nice, beautiful constant stress picture that we'd expect to get for that particular loading. Other examples of what I call blowout stresses. This is a panel I modeled and putting point forces in. I couldn't really get the overall distribution of stresses because it's just dominated here by these stresses. Now I can clip the contour back, and I've actually seen a couple of automated processes where the post-processor will clip them back for you. It kind of tries to recognize the singularity and then says, I'm not actually going to show the stresses around the elements around there. I really don't like that. If it's bad news, I want to see the bad news and then fix it up. Or just say, I've done the contour legend or contour levels myself to deal with that. And again, a methodology explained. This is an I-beam, and we do this in the Intro to FEA class, where I just put a load in the middle. And this is a direct axial stress running down in here. And it's building up. This is the actual triangular bending moment distribution building up, and hence the stress builds up in the same way. We expect to get extreme fiber stresses top and bottom the same. They are not at the top here. So what's happening at the top here, I've actually stabbed a load in badly right in the middle here, completely nonsensical kind of way of doing it. And I can see that bullseye there, what I call the blowout stress. So this is the actual nice gradation and transition through engineer serial bending, going through zero at the center. And it should go to negative. I'm sorry, it should go to positive equal to the negative there, but it doesn't. And again, it's because of that local bad modeling of however I'm going to get the load in there. I've just kind of ignored that and I've just stabbed the load in. So that local load application completely dominates the stress picture. Now, I wouldn't want to put that through in a report, but if I did, then again, I want to explain that's an FEA feature. Stresses around there are going to be useless to figure out what's going on. Further away, then they're okay. Again, our wonderful St. Venant's principle kind of comes into play there. This again is another example of high stresses. What I've done in here, this is basically a loaded latch or rim. I'm pulling down on this flange, I should say. Here's an even pressure distribution. That's the stress distribution coming up. The actual run out of the loading is just somewhere about here. This is actually constraining to ground. So this is glued to ground, infinitely stiff, and that's actually a stress singularity running through there. There's different scaling value. This is off to infinity. If I look at the actual XY plot, this is the peak value over here for the sensible approach. And I can't even plot on this scale what's happening for the singularity. It just shoots off to some crazy value here. So again, harsh stiffness transition. What we're implying here is that we've got stiffness which is infinitely stiff as we connect to ground, and suddenly we're running out to zero stiffness connected to ground. So no structure can ever do that in practice. There's no way you can actually achieve that. So in this particular case, it's better to apply the reactions back as applied loads there. So just beginning to wrap up now, this was one of my favorite location of peak stress. So we talked about feature stresses, we talked about stress levels, and now where is that peak stress? Well, many, many years ago, I actually had to do analysis of an ice hockey stick. And we were actually in, if you like, in competition with another consultancy who was also doing an analysis of the ice hockey stick, and then further work would follow. So it's a little bit difficult to figure out the boundary conditions. We've got two hands here holding the ice hockey stick. The blade, and I found this to explain what was going on. This is what I was told. You don't actually hit the puck. You hit the ice just in front of the puck, and then you're storing up a huge amount of potential energy, which is released through the puck. So basically, where will the peak stress be? Well, the boundary conditions are tricky because we're not clamping. So I guess a test article would just clamp here where the hands are. We've got soft kind of constraints where the hands are. It's a rather difficult thing to actually model, but for sure the stresses are going to be. You can imagine like a bending moment. If this was connected to ground, like I say, a pin joint, the bending moment would be peaking around this bottom hand in here. There is also going to be some stress concentration down in here as we're transitioning section through here. So the candidates could be here, I think, and around here. We did the analysis and we actually had a failure right against here because I think we put a fairly hard constraint in. So here or down in here is the peak stress. Now, if we actually look at ice hockey failures, I found these online and I'd never seen these before, and it's fantastic. Yeah, it's not exactly where the hand is. I suspect there might be some strengthening shaft or something in here, some difference in the makeup. You can see it's biased up to exactly where we thought it's going to be. Think about a bending moment diagram. Somewhere around here is where it's going to fail. And here's another guy. I guess it must be a bit of a shock when that comes. It's beautiful photography. So that's where it's going to fail. Interestingly, again, this is an operational experience. I'd love to know how that compares to the test loading that they do. So where did we say that we think our analysis is going to fail? We thought it's going to fail here. And just going to this diagram, this one here, our rival said it's going to fail here. And we thought, well, we don't know why it should fail there. There's no peak stress there. So the location of peak stress, from our view, wasn't there. In their analysis, it was there. Cut a long story short, we submitted this to the company. The managing director loved the opposition's result because he said, well, on test, that's where we get a failure right there. And we kind of puzzled. I phoned up the technical director and said, well, what's going on here? He said, well, we didn't tell you there's actually a splice in there. So the splice generates the stress concentration. And that's actually kind of a fabrication failure at that particular point. But none of you knew that. So I said, well, how come they got peak stresses there? So he went and looked at the model and he said, they're using a program where they've got a transition between hex mesh down in here, tet mesh down in here, and in that transition zone, the mesh in there, the element shapes are so horrible, is actually creating spurious peak stress concentrations there. I said, well, surely you're not going to accept that. And he said, well, no, but I'm being overridden by the managing director because he says, well, that's where it happened on test. This is where we see the analysis, and that was it. So I said to the guy, okay, well, when you come back to us, I'll give you a discount on the consultancy rate. And about 3 or 4 weeks later, came back and said, okay, everybody realizes what's happening now. So that was the interesting issue in that particular case. So that's, again, location of peak stresses. Does it make sense? Just to finish off that, maybe the rival competitor consultancy was analyzing this load case. So, okay, here under this load case, I can well imagine a failure somewhere up the body there. So, yeah, okay, but that's not the loading conditions that we've been given there. Now, I'm just going to finish off very quickly now with, in fact, let's see how many more slides I've got to go. I've got just a few more slides in here. So I've talked about the normal modes checkout. It's so useful. So as part of this checkout sanity check, as well as checking these maximum stress numbers, maximum deflection numbers, as I get older, I make more mistakes. I almost always commit my static analysis now and do a quick normal modes run on it just before I even bother to kind of check it out. So I'm going to add this in. It's such a powerful tool. It's a special analysis we do before a production run. Again, it's not designed to give any final answers. It's nothing perhaps to do with the analysis, but it's going to give us confidence in the results. Now, a normal modes analysis is very easy to set up. The only thing we need to make sure is we've got density on our material properties. As I mentioned before, then we get a mass matrix that goes with our stiffness matrix. We've got a dynamic matrix, and we can solve for if we've got rigid body motions, if we haven't, and it's just things flapping around in the breeze, as I describe it, then we're going to see that badly connected things in there. And I've come across a lot of people say, well, it's a normal modes analysis. That's dynamics. I don't have anything. I'm not a dynamicist. I don't know how to set these up. Well, every single user interface I've seen, as long as you've got the boundary conditions set up, that's the constraints to ground. You don't need the loading. You've got the right physical properties. You've got the mesh there. Just switch the analysis type to normal modes. Ask typically for 10 modes. Just don't ask for 1 because that's not going to give you enough information. Just flip it to a normal modes analysis. Try it out if you've never done it before. We're looking for the mode shapes in particular, and that's all we're interested in. Now, frequencies of 0 and clear rigid body modes mean, again, things not connected to the ground. So we're really interested in things flapping around, things badly connected. And it's a very, very easy to check to do. If you've never run a normal modes analysis, when you come off this, this presentation, you get a chance. Just flip the solution type. Got a static solution, just flip it to a normal modes analysis. It's going to pick up your boundary conditions, going to ignore your loading and just give you the mode shapes. And it's those mode shapes that we're interested in. Going back to that pattern there that I talked about, again, we ran this through and we could see some errors in the modeling here. The one on the right was interesting, and for you designers, this is an interesting exercise because this group of designers said, well, you can clearly see that, again, a higher mode there. I think maybe mode 10, mode 15, what it is. There's a lot of flexibility in that bottom plate there, and they all sort of got their heads together and say, who designed that? Who put the holes in there? Nobody could quite remember. And then clearly it's not producing very much stiffness. So they actually, on the fly, as we're going through it, the course, they kind of said, well, let's take that material which is there and apply it as a bottom flange to the longitudinals in here. And then we're stiffening the structure up. We're doing something useful with that structure. So when I'm teaching to designers, I really emphasize this as well. It gives you an insight into relative stiffness of the structure, and you may well find something like that. But usually we're concerned about things flapping around the breeze. So I haven't really shown it here. But well, here, for example, something not connected in properly. I've had plates which I expect to be clamped down on all 4 corners. Only one corner made it, and as we showed earlier. So that normal modes analysis can really show that lack of connectivity in there. Whereas perhaps animating a static deflection doesn't see that. This was off the same course. This was very embarrassing. I'm doing a quick demo. I modeled this with solids here, and I've modeled there's a thrust ram comes up in here, a big kind of thrust beam. It's just axial load and bending we're interested in. So I modeled that with beams. I was showing this, I launched the analysis, and bang, it wouldn't run. Now, rather than try and debug the static analysis to try and figure out whether degrees of freedom that were at fault, just run a quick normal modes. And this is just showing a screen grab of a particular rotational rigid body mode, clearly just flying around in space. Now, all that happened was I forgot to merge the bottom of the spider there with the top of the beam. So a quick 2-minute job, rerun the analysis, and away we go. So that's the kind of thing that we're interested in there. So that's it. I've overrun a little bit, but thanks very much for watching. What I'm going to be doing is we're going to be recording this, and what I'll do is clean up the video. I'll clean up all the ums and ahs, clean it up, and on the websites it'll be fully narrated. We'll put the Q&A in, and I'm going to curate the Q&A. On YouTube, as I mentioned, we keep it kind of quicker and sweeter because there's no tolerance on YouTube for ums and ahs or waffle. So look out for those links coming on later on. Next session is going to be a week from today, same time, same place, next Friday. And what I'm going to talk about there is free body diagrams, the importance of free body diagrams, some FEA examples of free body diagrams, and how they underpin our, again, thinking about how accurate results are, but also physically what's happening with the load paths there.